the algorithms that we already have, sort of atmospheric compensation or orthorectification or automated land use land cover, and they run those in order, or they upload their own algorithm, and then that gets run in the same chain with everything else. So this is configured for sort of national, state, kind of scale processing. It's not, you can run it on an image, and that works really well. But in this case, we're thinking about this as something where you're running in lots of whole scripts or over a big area. It's also configured for processing imagery as it shows up. So if you want to know every single time we collect and something happens like this, we will run the whole script for you as it shows up. This is the stack. Essentially, you start with the raw image. I've got tile here because I copied it from my other slide, so don't tell anybody. But this whole thing, orthorectify, compensate for atmosphere, pan sharpen, this is all defined by the user through an API. They simply specify the tasks they want run on the image and it runs. They can also upload Python code or C code or whatever it happens to be in the format of a Docker. And then that can also get run in the chain as well. And the output can be whatever the final output is, whatever the output of the code is. From an open source perspective, or from the OGC perspective, a huge chunk of this process is open source software. Lots and lots of pieces of this happen with things like GDAL, right? And so we are allowing the integration of those. This isn't 100% proprietary. This is, most of the things that we develop, have those components, but as a person who wants to do analysis on imagery, you can do a lot of development with open source code. And what this allows you to do is package those libraries into a Docker and then put them on a platform so that they'll run against the imagery and process it in the way that you would like it to be processed. So I'm just going to walk through one analysis example that I'm doing with this and talk a little bit about sort of how it works. So this is the Adelaide area in Australia. We're actually running a process where we're going to we are finding every building and all the attributes for the building, the roof materials and the size of the building and the height of the building, and does it have trees next to it, and what species, and all that sort of stuff, right? Getting digital elevation data for these. The challenge here is that all of these strips, because you can see for like a big urban area, you need a lot of strips to cover it, especially if you're dealing with temporal, right? So it does make sense to process these things at the strip level in some cases. They all show up at different times, right? They show up as they're collected, and we have to deal with them as they're collected. And so we've got this crazy, and I drew this, so I apologize, it's an eye chart. You don't need to read it, because there's only a couple of points here I want to point out. So all of these blue things are functions or tasks, right, you can run on an image. And all of the green things are data sets that get generated. And if it's a red thing, it's going out to somebody else, right? The data is being provided to a vendor, they're doing something and giving it back to us. And so the thing that's interesting about this, and the way that we've developed it, is that all of these things can run in parallel as the data show up. It's event-driven analysis. And so it starts off with a couple of AOIs and some Landsat data and some parcels, and then this green box here is an image is collected. And as soon as that happens, a task runs, these are orange, and it generates new data in yellow. And as soon as those data get generated, another task runs and generates data, and another, and another, and another, and we walk through this whole process of things getting kicked off because data shows up, right? And so in this way, we can really highly parallelize this process, where the two levels of parallelization are on the machine. If code is running on the node that spins up to do the task or set of tasks, you obviously can take advantage of the cores on that machine. So those are decided based on the complexity of the process. Some of these we spin up GPUs for. Some of these we spin up the little tiny, like half a K of RAM or whatever machines to do whatever the process is, right? So it's dependent on the size of the process. But they all run in parallel as the data shows up, so you don't have to really manage it. It's sort of like the way web applications are developed, where when a user does something, something happens. And so, again, this process is something that we use for, I want to process at the state level, or the national level, or anything we're really interested in getting the whole script. But again, what we've seen is that, and I don't know what to call it. I hesitate to call it anything because people get upset because terms are used in so many places. But I think of it as the new data science, or the new big data. Like a lot of people processing a lot of very small pieces of data to derive information, right? And it's all kinds of information. We want to be part of the process. We want to be accessible in the same way tweets are. And you just can't do that with a 30 gigabyte image, not easily anyway. And so this next paradigm, the second paradigm, which I'm eloquently referring to as parts and pieces, is tile-based. And so the idea here, as opposed to storing all the strips and then setting them up so that they get loaded on a machine and a whole series of processes happens. We're storing all of the data as very small objects. And these are, some tens of pixels objects, right, worth of data. But it's the full fidelity object. It's 16 bands, 16 bits, right? It's all of it that you can get off the satellite. We don't do anything to it. And then we either run one of our functions or one of someone else's functions on that little chunk of data, and then it gets output, gets consolidated and output. And so you can get those tiles and bring them to your local computer. You can get those tiles and you can put them on scalable compute, do something with them. You can get those, you can actually use that to calculate something and just get the knowledge straight from the platform, right? But it's tile-based instead of strip-based. And so it looks very similar, right? You'll see my tile over here. We start with this tile object, we chain these tasks together, and it's available through a REST endpoint, right? It's very, very similar to the process for the full strips. But because we have this set up as an object store, it's significantly faster and significantly more parallelizable, right? And it's also much cheaper for us to run. And so the thing, I don't know much about object stores a couple of years ago. Like, I've learned a bit here and there. So if you ask hard questions, I'll be sure to defer them to someone smarter than me. But my understanding of why this is faster is there's no indexing, right? There's no database, there's no compute needed to find anything, right? It's a very small piece of software that knows how the files are set up. And so this little piece of software sort of sits right here, and you say, I'm interested in this AOI, and it goes and gets all the tiles in that AOI, right? And it doesn't have to think about it to go get them. It just goes and pulls them off. And so because it's a very small piece of software, because it doesn't need any infrastructure, it can be parallelized itself. And so when you say, I want 300 tiles, like, one of the first processes is go get the actual tile that we need, and that just happens very quickly without having to hit anything else. And so that gives us this very high parallelization. The data is accessible at rest. And because it's very small, they're very cost effective, right? We don't have to spin up machines that have storage. It just all exists in RAM. So the processing all happens in these very small Amazon instances that are just RAM. And so we can spin lots of them up very cheaply and process these bits and parts and then bring them back together. And I think I've highlighted this in red so that I don't forget. The critical piece is that it's full fidelity. So you access this like a REST API, and you say, I want A, B, C, and D done to the tile. And if you need something that's yours, then you submit that beforehand, and then that's called F. And you just lay that out in the REST call, and it goes and gets the tile. And so in exactly the same way that, well, not exactly, but very close to the same way that people are accessing WMS images, like, you can access full fidelity data that's processed the way that you need it to be, and ready for you to do something to, or it simply provides the answer, and that's what comes out of the process on the tile. And so I wanted to outline just a very simple example of how this might work in what I think of as like modern data science. And so this process begins with somebody saying that they want to train a model, right? So they want to train a convolutional neural network, and they provide whatever model they need to us ahead of time, right? We've got a mechanism for loading these things in. We usually use Dockers, but there's also configuration files for different types of models. And so the first thing that they're going to do is they're going to need tiles that are optimized for looking at, right? Doing air photo interpretation, if you're into that sort of thing. And so they essentially connect to the object store, and they hit the API that connects to the object store, and they pull all the tiles they need to actually look at the pictures, right? And when they do that, they're drawing all their features. Here's an airplane, here's a boat, here's whatever it is. And then that gets stored in any vector store. Once that's done, those can be used for training the model, right? The model's there, the vectors are there, so they run a request that says, now train my model with my vectors. And then once that's in place, it's very easy to just request areas that you run your trained model on, right? Here's this area, this area, this area. They're going to use the training from other places, but it's only as good as the training. But this provides the whole mechanism for doing it. And I think the thing I wanted to point out here is, in this first step, you're getting these tiles optimized for imagery, right? They're pan sharpened, they're very low weight, like 0 to 255, RGB. But then when we do the actual model training, we can get very different tiles, right? We can get a different process applied to those so that they're trained on full fidelity data, like with 16 bands instead of 3, for example. And then that model gets run with whatever the full fidelity data is that's needed to exercise essentially the model with the features. And so the paradigm of this parts and pieces and machine learning, it supports feature extraction, but it also is it's much easier to integrate into a traditional data science or traditional big data process, right? You're running all these things in Hadoop or Spark or whatever. You've got 1 billion processes and 100,000 of those need something. And so 100,000 little requests go in for little tiles and then come back and you get the data, right? So it's set up to be able to integrate into more of a traditional data science process. And now that the data is smaller, we can sort of map it and reduce it all we want, which is very hard to do with big data. And essentially we're calling this knowledge from imagery directly as a service, right? Especially if you've got your own process that you want to run on these tiles, you can call that and say, I don't want a tile, I don't want an image, I want the knowledge that I'm actually trying to extract from it. Rather than calling somebody on the phone and saying, I'd really like to order a strip and it's very big, can you put it on a DVD and ship it to me? Which is what we were doing a few years ago. So, just to kind of summarize a little bit, and I'm hopefully ending a little bit early, so we'll have lots more time for questions. But we're looking at where data science is going and where big data are going and trying to figure out how we can meet it halfway. And so, as opposed to saying, go to NGA and get the imagery, or go get a DVD and get the imagery. We're trying to make sure that imagery isn't seen as the difficult part of machine learning, right? It's seen as a very convenient part of machine learning and data science. And we're essentially trying to balance this traditional image science community, which is looking at, we've been doing LULCs forever, we've been doing feature extraction forever, and we know how to do it on these big scripts, with this new sort of computer vision community that doesn't really care about scripts and is looking at other types of formats. One of the ways we're doing that, and I wish I had prepared more on this, I apologize, I'm not as directly involved in SpaceNet. You guys may have heard of this. Here you go. But we're essentially providing several thousand tiles that have known features in them, and we've identified the features for you, and it's out there on the cloud, essentially waiting to be used for development of machine learning methods, right? So you can go and access that. Other people can go and access that. You can actually compare models by detecting features that are derived from the same imagery, that sort of stuff. It's a really cool idea. We just kicked it off, but I think it's fun to think about what we could do with that, how this integrates with some of the other things we're talking about, and as we start to think about the next steps with test beds with OGC, does something like this apply? Like, is this something where we can start to work it in a slightly different angle and really make it? Is there a way to make it even more useful, rather than just as a tool for the data science community? Is there something bigger we can do with it? So this is my favorite building in Australia, because I think it looks like the Hawaiian Punch guy. And that's what I have for you guys today, but I'm actually quite happy to answer questions.
Have you looked in SpaceNet for others?
Pardon me?
Have you looked in SpaceNet for other buildings that match this map?
No, but that's my weekend. I think I just lost my weekend. Thank you. Yes, sir. Oh, I'm sorry. You go ahead.
So suppose I want to use something like an NVIDIA DGX1 to do the deep learning training. How can I do that in your model?
That's a great question. I'm sort of intentionally not talking a lot about like the DG sales pitch, because I don't want really to go that route. I'm a lot more interested in thinking about how we can develop things kind of as a community. But the answer is, when you sign up to use the platform and you specify a task, especially one that you're running, you can specify the domain that it runs in, right? And the domain is the Amazon instance that it runs on, right? So there's various sizes and shapes of those, and the GPU is one. And so you can specify that your process runs on that domain, which is the GPU machine.
So I don't know, does Amazon have the latest NVIDIA low fidelity GPUs and things? I mean, I'm just a little... I see how your architecture works for sort of commodity, well-established tasks, but for things like deep learning...
Yeah, so I think there are several communities that are doing deep learning, and some of those communities are a little bit more tied to specific technologies. And so your specific question about what's on Amazon, I feel like NVIDIA and that doesn't really keep up as well as it should. I know that we're working with Amazon every time something gets released to try to find out when it's going to be available, and we're trying to keep up with what's happening there. And I know that there are limitations to what you can do on Amazon, but the other side of the equation is, this is the lesson with working at DOE for 10 years is, I've got a supercomputer, and it's awesome, and I can do whatever I want with it. And nobody else can, because nobody else has one. And so we're trying to figure out how we can make as much accessible as we can, given the limitations of the current cloud infrastructure. So another person had brought up the risks of buying into a cloud infrastructure, right? You buy into a cloud infrastructure, and if something changes or you need to leave, then you have to figure out how to code it so that you can get out. And we struggle with that quite a bit as well, because of issues like this. Well, should we put it there? I mean, what if we need to use the latest NVIDIA drivers? And the answer is, it's like this 80-20 thing, right? We put a small investment in, we modularized everything so that we could re-architect if we want, but we need to run it. And a lot of other people need to run our stuff on it. And so that's the solution that actually gets us out the door and gets things running and gets analysis happening. So.
I'm interested in use cases. So at the very beginning you talked about the types of people who might use the platform. So you went to the